Andre and I want to talk about the art of origami. Hi, I'm Andre Wiederkehr, and I want to talk about the math of origami. So, basically, hi, I'm Andre Wiederkehr, and I want to talk about the mathematical art of origami. When people hear the word origami, they often think of something like this, the classic crane. And when they hear math, they think it's more abstract and not as beautiful, like how to fold a paper into fifths or sevenths, or how to fold a rectangle with the dimensions of 1 by the square root of 2. And these things are beautiful too, but in a more abstract mathematical way. So one thing that I really enjoy is a type of origami which combines math and art. And that is modular origami. Modular origami is just a type of origami where you have a bunch of edge units like this, and you just join them together with flaps that go into pockets to form more complex shapes like this. So modular origami, the models range from models like this, the one I first showed you, to much simpler models to much more complex models. But the type of modular origami that I want to explain is called polypolyhedral origami. So basically what I'm going to be doing is walking through the procedure for how to enumerate every single polypolyhedral origami model. And the term polypolyhedron was first coined by Robert Lang when he tried to enumerate every single one, and he did succeed. So to run through the conditions for a polypolyhedron is, number 1, there has to be more than one polyhedron. One polyhedron, more than one polyhedron. 2, they have to be topologically linked, like this, not like this. 3, all the edges have to be uniform, so they all have to be mathematically equal in the structure. That means they have to be the same length and they have to hold the same position in the structure. This one doesn't count because this edge does not hold the same position as an edge down in there. Whereas this one, it does count because all of the edges hold an equal position mathematically in the model. If it weren't for the color, you wouldn't be able to tell them apart. And 4, this is for the practicality of actually constructing them, the edges can't intersect because in reality, we can't have things actually going through each other. Okay, one thing I have to warn you about, before we try to enumerate them, because of the time limit, I don't really have time to explain every single term or give every single proof. So I'll just explain the concept without the proofs or detailed equations. Okay, now on to the enumeration. The way we're going to enumerate them is by a property called rotational symmetry. Now this is based on the uniform edge requirement. Basically, a structure has uniform symmetry. I'll use this as an example. If you can turn this edge into coincidence with another, where another edge was, like that, and the structure remains unchanged. See, it looks just the same as before. Now, that structure has rotational symmetry along that one axis. But if we found all of the different axes that that structure has rotational symmetry on, we would know the group of that object. Because there are only 5 three-dimensional finite rotational groups of symmetry. Now the first 2 rotational groups are made up of rotations that are all in one plane, and we can't use those because we're trying to make 3-dimensional shapes that have rotations in 3 dimensions, not in 2 dimensions. And if we have just rotational symmetry in 2 dimensions, then all of the edges will be in the same plane, and then they'll either intersect each other, which does not work, or they won't even interlock, which also does not work. So we can throw out those 2 groups immediately. They're called the cyclic and dihedral, but they're out. Okay, so on to the ones that we care about. The first one, the tetrahedral group. Now we saw this one before, but the way that you can quickly calculate the number of different rotations in a rotational group is you count the number of faces on the object, and then you multiply it by the number of sides. This one has 4 faces and 3 sides on each face. So 4 times 3, 12 different rotations, unique to the tetrahedral group. The next one is the hexahedral or octahedral group. So, a hexahedron has 6 sides, each side has 4 edges, therefore you have 24 different rotations for this group. Works with an octahedron too, because it's the dual. This is a property that you might have to research on your own time. Basically, an octahedron has 8 sides, and each side is a triangle, so 3 faces, 8 times 3, still 24 rotations. The next rotational group is the dodecahedral or icosahedral group. So, if we use the dodecahedron as the example, a dodecahedron has 12 faces, and each face has 5 edges. 12 times 5 is 60, so it has 60 different rotations. Works with an icosahedron too. An icosahedron has 20 faces. Each face has 3 edges. 3 times 20 is still 60. So, those are all of the finite rotational groups. Okay, so you're probably wondering, how is all of this rotational symmetry group stuff going to help us construct all of the polypolyhedra? Well, we'll start with a thought experiment. Say we have a point floating in space and we apply a tetrahedral rotational operator to it, so it goes like that. Now it's down here. And then we apply all of those rotational operators and we get a series of points, and those points are called an orbit of points. Now that orbit is generated by that first point and the rotational operators that we applied, the rotational group that we applied to that point. Now, there are basically 4 types of points that we could sort of place on our imaginary tetrahedron that we're moving around here. We could put one on the vertex, and then there are 4 vertices, so it would generate a total of 4 points. Or we could put one on a face, and since there are 4 faces, it would generate 4 points. We could put one on an edge. There are 6 edges, so that would generate 6. Or we could put one somewhere else, somewhere that's not on a vertex, not on an edge, and not in the middle of a face, somewhere else on the face, and then that would generate a total of 12 different points, unique points. So those 4 types of points on an imaginary shape, we'll call them V for vertex, E for edge, F for face, and C for complete, because it does every single rotational operator. Every single one of those generates a new point. Okay, so this is the numbers of points that we would get if we applied a rotational group, one of these rotational groups, to a V, E, F, or C point. Now, we can remove these groups altogether because we know they're all on a plane, and that doesn't produce any polypolyhedra. However, we have all of these points that we need to think about from now on. Okay, we have our first classification. But how can it help us build a complex model like this? Well, here's where the uniform edge thing comes in, because if every edge is mathematically equal to every other edge, then by picking an edge, we'll call it a seed edge, and rotating around, we'll get every other edge in the model. Okay, so if we take one end of our seed edge and apply a V, E, F, or C type of orbit to it within a rotational group, we'll get a floating orbit of points. If we take the other edge in the same rotational group, but with any V, E, F, or C orbit, apply that, then we get 2 orbits of points. If we join them together and we get polyhedra that are walking together, we have a polypolyhedron. Do that for every single possible set of orbit operators, and we have every single polypolyhedron. Okay, we're done enumerating, right? Well, that'd be a little too simple. Okay, so there are a few factors we need to look at yet. And first of all, I'm going to define our side notation system. So this is for an edge. O1 is the orbital type of point for one end of the edge, V, E, F, or C. Now, O2 is the type for the other end of the edge. That's also V, E, F, or C. 4 times 4 is 16. 16 different possible edge types. Now, say we had, for example, a VV. We have our tetrahedron here. Let's say it's a vertex, right? And the V1 is right on this radial distance. V2, let's say it could be drawing points way out here. We could have our 2 orbits have different radial distances. So if the radial distances are the same, we'll call it V1, V1. If they're different, we'll call it V1, V2. Now, if we swept the value from the ratio of the radial distances being the same, 1 to 1, to being 1 to infinity, if we swept that value mathematically across, we would come across several more polypolyhedra. And so we can do that for V, E, and F, and C gets a little more complex. Here's the deal with C. So remember how I defined the C-type point as being any point that's not right in the middle of the face here, so this is somewhere else on the face? That means we can put it anywhere on the face. And of course, if we can do that, that's going to drastically vary the angle of the edges in the finished model, maybe how they link together, maybe even how the polyhedra weave together into the final polypolyhedron. So this factor is incredibly important. And mathematically speaking, that's just a one-dimensional property, and this C thing is a 2-dimensional thing that we have to watch out for, because there's that, and there's still the radial distance thing. So if we combine those, make a 2D plot, for example, we can see all of the different polypolyhedra that we can make, all of the new ones. And so, once we've done that for all of our different rotational groups, we actually have every single last polypolyhedron enumerated. Time to go do some folding.